with Darrin Speegle, who will be talking on dilations and orthonormal wavelets.
Thank you. It's very nice to be here. I appreciate the invitation very much. I thought a little bit about what to talk about, and I decided to do, perhaps because my odometer rolled over recently on my fly, I decided to do a little bit of an overview of kind of the research that I've been doing in this area in the last 12 or 15 years, rather than talk about just new stuff. So this is really more of an overview talk of this topic than just really anything particularly new and exciting that I've done in the last 6 months or a year. It's about dilations and orthonormal wavelets. So let me just start Let me just start by reminding you what I mean by an orthonormal wavelet. Probably everyone knows, but perhaps not. You probably don't think about it in this generality. The orthonormal a wavelet, for this talk I was calling a wavelet, is a function L2 such that when you dilate it by powers of some invertible matrix A and translate by integers, we'll say, you get an orthonormal basis for L2. Right. So this is probably more general than or less general than maybe Polly thinks about it, but more general than many of the other we think about it, because I'm not even assuming that we have integer matrices, or a priori I'm not assuming the determinant is it's not equal to 1. I'm just not assuming anything about the dilation here. I can also not assume anything. You might say, well, you're assuming something about the translations, but if you get a change of basis, this is still a general case. Right? You can either, this is just a general case of the integer translations. If you're willing to consider all matrices, then the integer translations are the general case. And the general question that has kept me busy is just the first question you might ask, having seen this definition, right? So, which matrices A are there A wavelets? Right? If you show this to someone, this would be probably the first question that they would ask. So, the first example, and the fundamental example for the type of work I've been doing on this area, is not via the wavelet in the time domain, but rather actually taking the Fourier transform. So I just wanted to mention, that you probably all know, that the Fourier transform, the translations become modulations, and the dilations by A become dilations by the transpose. Since I'm taking J to call integers, the transpose. And the first example is just the following, right? You take K be this interval, and you look at the indicator function on that, and we can see that this is that the Fourier transform of a dilation by 2 wavelet is the standard dyadic wavelet, because modulations form an orthonormal basis for L2 of this interval, right? This is just like this is just L2 of the circle. I took a piece and moved it over a little bit, so it's still going to be an orthonormal basis for L2 of this set. And the second part is that when I, well, B is equal to A here, but the second part is that when I dilate this set by powers of 2, it covers up the line with only little intersections like single points, or the intersections have measure 0 is the important thing. So it's a measurable partition of the line when I translate by integers, and also when I dilate by powers of 2. And if you think about this, this doesn't depend on the exact dilation I'm using. If I have a set, I think this is on the next slide. If I have any measurable set, well, it needs to be I guess it needs to be well, it will be a finite measure. I have any measurable set whose translates partition or RD, and whose dilates partition RD, then I will get that is a Fourier transform of an orthonormal wavelet. So, if we're thinking about the general question, which is for which matrices there exist orthonormal wavelets, the question you might ask is, well, okay, for which matrices do there exist this particular type of wavelet? I'll call a set K that satisfies as a wavelet set, and the indicator function on the wavelet set is the Fourier transform of a wavelet. Okay, so that's the question I want to think about. So here's a lot of, so the point of this slide, there's a lot of symbols on this slide, is that the problem is completely solved for the line anyway, right? So it's completely known for which dilation factors on the line there exist wavelet sets. Namely, I'm restricting to A's bigger than 1 in absolute value, because the definition was symmetric in, I mean, it was A to the J, so it's symmetric in A and 1 over A. So this is the general case. So if A is less than -1, or if A is negative, then I get a single interval A, which is a wavelet set. If A is equal to n plus 1 over n, so it's like 2 or 3/2 or 4/3, then I have a 2-interval wavelet set. And if A is not one of those two things, then I get this crazy-looking 3-interval wavelet set. And these are the minimum number of intervals that you can use to create wavelet sets for the 3 dilations. Now, many people who are coming to this from kind of from applications or from just the traditional way of thinking about it, probably think, that might be surprised, I guess, that, for example, if you take an irrational number here, that you can still get an orthonormal wavelet. This is because normally you think in terms of MRAs, and you think about dilation by 2 or 3, perhaps, if you're willing to have multiple scaling functions, this kind of thing. And so I have here a little, I picked A equal to pi, and let's see if this works. I hope it does. This is what I'm doing on my own computer. And I made a little movie of this is the set, that was fast. So the start set was the wavelet set when A is equal to pi. I just did the, I'll run that again. I'll run it a couple times. So the start set, this was the wavelet set was equal to pi, and now I'm just doing translations of this to show that the translations really do look like they tile the line. And then I have another little movie that'll do the dilations. Right? So this is with the B. And so you can see that the dilations also, at least, it looks like they tile the line. I'm not sure how convincing, but they're convinced all the way to the end of it, but that's they tile the line. Okay. And I didn't know whether MATLAB was going to work here because it's really tricky. It doesn't work, always work, so I had these also. I'll have it skipping a lot of those. So now we want to go into higher dimensions. And so the first question you would probably want to know the answer to for thinking in higher dimensions is, well, for which matrices does there just exist a set K such that D to the JK is a partition of R to the D, right? This is already a question that maybe you haven't thought about and don't know immediately the answer to even this question, right? And certainly in the wavelet set, it has to satisfy 2 conditions together. So there are there's a lot known about this, but the 2 I want to mention are that you can get a bounded set K that is a partition of R to D if and only if all eigenvalues of B are greater than 1 in modulus. And then you can get a set of finite measure if and only if the determinant is bigger than 1. That should be an absolute value. The absolute value of the determinant is bigger than 1. So we see we have a restriction on the type of matrices that can lead to wavelet sets. Namely, you have to have, if you want to get the set K needs to be a finite measure, and so we're going to have the determinant of our matrix not be equal to 1. This is, I think people would have been willing to grant that to me. All right, so there are several methods for constructing wavelet sets. And I have some pictures that correspond to each of these methods. For the determinant 2 case is the easy case. Okay? This is the easy case in R2. Right? Here, for the determinant 2 case, what you do is you look for a set T that tiles by translations here. And, okay, this is the tricky part, such that T is contained in BT. Right? Now, if you've seen expansive matrices before, you know that there always exists, for any expansive matrix, I should say this should be an expansive matrix here. So, for any expansive matrix, you can find an ellipsoid which satisfies T is contained in BT. Here we're looking for something a little bit stronger. We're looking for, or different, I should say. We're looking for a set that tiles on translations such that T is contained in BT. And again, I have a couple of, have an example of that. I'll skip one of these. All right, so this one, let's see. So here, this the original parallelogram was my set T, right? I expanded it, and the two triangles here were my sets, was the wavelet set. There's the triangle. So this is my wavelet set, okay? And then I'm showing you that yes, this does indeed tile when you apply dilations to the set. This was the matrix. I think it says 0, 2. It was determinant 2, trace 1 was the matrix. Right? And then for translations, well, translations for this one are pretty easy. You have a triangle like this, a triangle like this. If you move this to the right one, you get a square, and we know the squares tiled by translations. Okay. Now, the second way is that you can do there are iterative procedures for constructing A wavelet sets for when the matrix is expansive. Right? And I wanted to show you one of those. Let's see. I think I'll slow this down a little bit. Okay, so here's the iterative procedure. Start with a set that tiles by translations. That's just too fast. Okay. Now, I'm trying to get, I'm going to slow this down. All right. You start with a set that tiles by translations, the square. And I know this doesn't compose to tiling by dilations at all. So what I need to do is I need to change this. I'm going to cut out a piece in the middle and make it look like a square annulus here. Right? So if I take this piece and I move it somewhere, or if I just removed it, then it would be a square annulus that tiles by dilations. So where I'm going to move this is I'm going to split this into two, and I'm going to move this one up to the top, and I'm going to move this one down to the bottom. And now this will still tile by translations, and it comes closer, at least, to tiling by dilations. It doesn't yet. So I need to get rid of the piece in the middle here when I divide by 2. Right? Now it no longer tiles by translations, so I have to add a piece. I'll take this and I'll add it down here, and I'll take this and add it up here. Right? And then I will iterate this procedure until I get something that looks like a wavelet set. So here's skipped a couple of steps, and then one more. You'll see that this is starting to look like a wavelet set now, because if I step one more here, right? If I dilate this, it fits pretty much here. If I translate it, it fits up here, and so on. And so this is the iterative procedure, and for dilation by 2, it was thought, right, that this was this was already kind of a surprise, I think, that by dilations of 2 times the identity, that you could get a single wavelet. Well, a lot of us thought about this, and we came up with all kinds of variants on this iterative procedure. I only mentioned a few names here, but many people thought of different variants on this iterative procedure. And then, a couple of years ago, Kathy Merrill came up with a new technique for doing this, and she was just really clever, right? And so I'll show you hers because well, I think it's amazing. Right? This is dilation by 2, and I'll speed this up again. So here's the set that she came up with, and I'll show you here's the dilation tile that it leads to. Right? So when you just dilate by 2, it leads to a nice, pretty dilation tiling of the plane, and then translation is similar. Right? Yeah, I can't show all. I didn't show all translations, but again, I forgot to close that. So translations, I just showed several of them. When I start translating, you see it starts to fill everything. It starts filling up everything by translations. I forgot to fix the axes, so this looks a little bit. and the translations fill everything up. And this was an amazing example because the yellow is the wavelet set, and you can see it's the union of, you know, 3 really nice simple objects. And really, in all honesty, well, okay, I'll speak for myself. I didn't think this was possible. When you see it now, everybody says, come on, how could you have not seen this? It's so simple. But at the time, I honestly didn't think it was possible. But once you kind of get the picture in your mind, it's not so hard. Okay. Like I said, I didn't know whether those were going to be. So the one theorem that I'll mention here is that if you have any expansive matrix, so remember, I'm not assuming integer value, I'm just assuming that all the eigenvalues are bigger than 1 in modulus. Then you can always get an A, there always exists an A wavelet set. Okay. And the proof of this is an iterative procedure, a little different than the one I showed you, but it's a family. Okay, so now we get into the nitty-gritty, right? So what about this spectrum? Certainly not all eigenvalues are bigger than 1 in modulus. We can agree to this. This has eigenvalue 2 and 3/4. This one, it turns out, there's not a wavelet set that corresponds to this. And the reason is, I get a proof there, but probably. The reason is you start with this. This is from negative a half, positive a half to 1. And you look and see, well, how much, so what, if I'm trying to construct a wavelet set now. How much of the set can I put between negative 4th and negative a half? Or positive 4th and positive a half? Well, if it has to tile by translations, the height really, for almost every x, the height can only be at most 1. And so the measure of the set here has to be less than the width of the interval down here times the height, right? So that's a 4th is all you could put here, an 8th is all you could put here, a 16th is all you could put here. And then on the other side, well, the total measure of the set is less than or equal to 1, so I can put 1 here, 1 here, 1 here, and so on. And the problem with this is, if I start mapping whatever, I don't know what this set looks like, but if I start mapping it back over to here, it's going to have finite measure, right? Because of the way we've got the thing set up. Well, so it's not going to cover up the whole plane if when I map it into this little strip, it's only got finite measure. So the problem is that the eigenvalue here, or the eigenvector I should say, is in the exact same direction as the direction that we're translating, right? That's the problem, is that the eigenvector is in the same direction that we're translating. Well, using that as kind of a place to look, really, Rick Laugesen asked me to try to come up with an example of a wavelet when we have eigenvalues on opposite sides of 1. And so using this as an example, I thought, well, if instead of, maybe if we had an eigenvector that had an irrational slope or something, right? Then we'd be pushing things up in such a way that that this obstacle would be eliminated, at least. And maybe, if we're lucky, we could force things together in just the right way to get it to tile by dilations and by translations. And it turns out that was correct, and even more than I thought. It kills me to put these people's names up here. I'd ask you to name. I like them both, but they took my example and realized that I had overlooked that I'd actually characterized it, and I just didn't. There was like one little thing that I hadn't quite realized. Dang it. So they have this really nice theorem. I really wish I would have been one. I really wish I would have Speegle like that. This is really ionized. So they completely characterize the matrices A for which there exist wavelet sets. Right. And it's exactly what we were talking about. So the tricky part was when you have one eigenvalue bigger than 1 and one eigenvalue less than 1. And there, it's exactly if the slope of the eigenvector is irrational. Right? That's exactly the conditions you need in order to construct the wavelet set. Slope anyway, yeah, the item there. So I point out that this problem is still open for argument. Right? We don't know which matrices in R3 you can find a region that tiles by translations and by dilations. And it's not known, for example, whether here you can construct a wavelet set that has non-empty interior. So these sets are really, really weird. They contain no circle of full measure. I mean, I know we're thinking of measurable sets, so it's not kosher to talk about interior, but you know what I mean. So this is an open question. Okay. Now, returning back to the original question, for which matrices exist A wavelets? Askew and Wang didn't finish the whole story, right? They just said, which matrices do there exist wavelet sets? Which I certainly believe that the answer to that question is always going to be the same as for which matrices do there exist wavelets. I believe that, just like I believe that there are no nice wavelets for dilation 2 in the plane. I believe that in the exact same way. So that we return to this question and say, well, okay, we have to try to answer the original question. Which matrices do there exist wavelets? Well, the problem is, there are nice characterizations of wavelets, so so we need to have characterizations of wavelets in the plane. And I want to talk to you a little bit about characterizations of wavelets on the line, right, in order to motivate the characterizations of wavelets in the plane. So, returning back to the dyadic case, it's relatively easy to show that the wavelet system generated by a function C is orthonormal if and only if these two conditions hold. So this is just to Fourier transform and periodize, and it's not too hard. Now, I want to try to motivate a condition. We'll see how it goes. This is the first time I've tried this in front of a group. I like this motivation, but I'm not sure. We'll see. All right. So suppose that C has support is contained in this union of intervals, for example. All right. So this is like for classical Riemann-Mayer wavelets have this support for the Fourier transform. Let's consider this matrix that's defined for all C in the interval -2/3 to -1/3. So notice that C plus 1 is 1/3 to 2/3. This covers up 2/3 to 4/3. This covers up -4/3 to -2/3. So this covers the whole support of the Fourier transform. Okay. So now remember what the conditions on C hat were. They were that the sum of the squares of the rows were 1, and then if I multiply this times this bar plus this times this bar, I get 0. So that says it has orthonormal rows for this matrix. Well, as you know, right, that means it also has orthonormal columns. So what are the conditions that correspond to that? Well, the general conditions that correspond to having orthonormal columns are these in terms of wavelets. So these, in some sense, I'm lying a little bit here. I don't know how to make this proof precise, but in some sense, these conditions are equivalent to taking just the normal conditions for orthonormality of dilations to translate, and saying, well, instead of having orthonormal rows, we have orthonormal columns. So these are two more conditions that have to be satisfied in order for a wavelet to, for a function to be a wavelet. And in fact, it's enough to know that these two conditions hold, and only one of the third, for example. There's a lot of stuff about this, but this is where I was headed. So we have this condition and this condition. Well, if you think back to the argument that I gave over here for 2, 0, 0, 3/4, if you think really carefully about what I said, we've actually shown that there can exist no function C in L2 of R2 that satisfies the so-called Calderon condition and also satisfies this periodicity condition. You have to do a little bit of work, but that's essentially what we've shown. is that no function can satisfy these two conditions, which are two of the three that you need in order to be a wavelet. Now, this is where the gap is in showing that the characterization of wavelet sets is the same thing as the characterization of wavelets. We don't know whether those conditions are necessary conditions for all dilations. All right, so that's what we would have to do in order to finish the proof, is we would have to show that the two equations, above, are necessary in order for C to be an A wave. And in fact, it's a little embarrassing that this problem is even open for the matrix I've been talking all the time about, for the diagonal matrix with eigenvalues 2 and 3/4. It's open even for that matrix, which is embarrassing. But the reason that it's open is exactly because there are no nice sets that tile by dilations, really. And so you use that a little bit implicitly when you go to prove that those conditions are necessary. Kind of implicitly, you use the fact that you have nice sets that tile by dilations and translations. And so if you don't have that in this case, that kind of explains why it's a little bit harder to show that these conditions are necessary for that matrix. Okay. I didn't know when I prepared this talk, I didn't know whether my movies were going to work. So I prepared really two talks simultaneously. One had me going on and doing something else, but the movies didn't work. And since the movies worked, I think I should stop. Thanks.
Are there any questions from the speaker?
Is that one of the because the books out there has had it, and now it's